Today we'd like to start talking about energy conservation, including heat. So we've already learned about energy conservation. It's one of the most important ideas we learned all year. So today we want to expand it to include heat. So I want to remind you of your reference sheet that has all your important information that we've already talked about, the specific heats, the heats of fusion, and the heat of vaporization for your different materials. I want to remind you about your graphs where you have solids, liquids, and gases, and you have the formulas to calculate the heat for each of those different phases. So for region A, C, and E, we would use our formula Q equals Cm delta T. When we are melting, that would be region B, we'd use our heat of fusion. And when we're boiling, we use letter D, which is our heat of vaporization. If instead we are cooling something down, we do the same formulas. This again is for the pure phases, gas, liquid, and solid. The heat of fusion is now for freezing, that would be letter D. And the vaporization would actually be for condensing. So these are the different formulas for the different phases and phase changes. Okay, so today we want to remind you that energy conservation is the idea that energy cannot be created nor destroyed, but it can change form and it can transfer from object to object. And we learned about potential gravity and kinetic and elastic before. And we've already talked about this year how kinetic energy can turn into heat as friction slows an object down. We can see this with the brakes of our car. Every time we apply the brakes, the brake pads and the rotors get really hot as all the kinetic energy of the car turns into heat. We can also see this, we're not going to actually do this problem, but we could also see this when we drop objects like this ball. And after it hits the ground a few times, you'll see that the temperature of the ball has gone up. We've turned our potential energy, gravity, into kinetic energy, and when it hits the ground, it's going to turn into heat. Okay, our focus for today is kind of what we did in lab, and that is mixing two objects together when the two objects start at different temperatures. So we are going to have a cold fluid, and we are going to have a hot fluid. We are then going to mix them. And what we want to do is we want to track the temperatures of these two materials as we combine them together. And we'll get a graph that looks similar to what you saw in lab. You'll see here is where it plateaus, so we now know that we're measuring the temperature of the hot water and the cold water. And then we mix them, and we can see the hot water starts dropping in temperature, the cold fluid starts rising in temperature, and they are eventually going to hit the same temperature. We want to stir this to make this happen quickly. When they meet up, this is going to be called thermal equilibrium. They're going to stop exchanging energy. We're going to have one object lose energy, and we're going to have one object gain energy. Both of these energies are in the form of heat. So we're going to have our hot water lose heat. That's going to turn out to be a negative number. And we're going to have our mystery fluid that started out cold gaining energy. And the big idea is that we cannot create or lose energy, so that the heat that is gained by the cold will be equal to the energy lost by the hot. Now, because the energy lost by the hot is negative, we're going to put another negative in front of that to turn it positive. So we have heat gained is equal to negative heat lost. This is our big idea for today, and make sure you understand it. It says that when you mix a hot and cold object, one object gains energy, one object loses energy, but the net energy remains the same. Obviously, in order for this to be true, we need to be working in a styrofoam cup, or other insulated environment. Otherwise, heat will be lost or gained from the environment. But if we have this take place quickly, or we do it in an insulated environment, heat gained will always equal the negative of the heat lost. Okay, so let's work through the mathematics of this. Okay, our hot water has a mass of 150 grams. That's about 150 milliliters. And the cold fluid, and we don't know what that fluid is, has a mass of 300 grams. Okay, so what we're going to do is we're going to get the temperatures right before we mix. So we have about 72 degrees Celsius. We have about 6 degrees Celsius. And they meet up right around 42 degrees Celsius. All right, so what you're going to do is you're going to say the heat gained is equal to the negative of the heat lost. Lost is going to be the hot water, so I'm going to write that right above. Gained is going to be from the cold fluid. The cold fluid is gaining the energy. Because there are no phase changes, both of these will go by the same formula. Cm delta T, Cm delta T. We know this. We can look it up on our reference sheet. It's going to be 4190. Mass, make sure you work in kilograms. And then temperature change, you're going to do 42 minus 72, which would be negative 30 degrees. Again, the hot water has a negative temperature change because the temperature is dropping. Remember, there's a negative in front, and those two negatives will cancel out. For the cold fluid, we again subtract. And we get 36 degrees. We get a mass of 300, and we solve for the specific heat. I'm going to allow you to finish that math on your own, okay, and hopefully you understand how we approached this and how we got our answers. Okay, we might sometimes have different phases, so in this case we have hot water and aluminum. Neither of them are changing phase, so we can again write our Q gained equals negative Q lost. Gaining again, this time the aluminum is cold, so we're going to have the aluminum gaining and the water losing. We're going to do Cm delta T. We're going to do Cm delta T. And this time we're trying to figure out how much hot water we need to raise the temperature of the aluminum to the 63 degrees. Make sure you use the specific heat of aluminum, so you can look that up on your yellow sheet. Make sure you're working kilograms, and make sure for your delta T, you use the change for the aluminum. For the hot water, you're going to be using the value for water, which again is 4190. You're solving for mass, and the temperature change here, you're going to use the temperature change of the water, so 84 and 63. Again, the delta T is going to be negative. It's going to cancel with the negative in front, and you're going to be solving for M. All right, so I'm going to leave that for you to work out the details. Finally, we're going to do one that involves phase change. Okay, so this time we're going to take a thing of boiling water, and actually by the time we get it to where we're going to use it, it's going to drop to 90 degrees Celsius, and we're going to see if we can melt some ice. So this time we're going to have a phase change. We always are going to be using our heat gained equals negative heat lost. Gaining is going to be the ice. Losing is going to be the liquid hot water. The ice is melting, so we're going to use the formula MHF. And for the hot water, we're doing Cm delta T. We know the C value. For the mass, hopefully remember for water, 3 liters would be the same as 3 kilograms. And the temperature change of the water is going to go from 90 all the way down to 0. There is so much ice in this pond that we're not going to have the water heat up. In fact, we did not even melt all the ice in the pond. Okay, so the water temp is going to go from 90 to 0, so it's going to drop by 90 degrees. Okay, look up the heat of fusion of ice and solve for M. How much ice can I melt with my water? Okay, I know this was a lot to work through, but I'm giving you 2 days to get these notes complete. That means have them in your notebook and work through all the mathematics. This should be done by the end of the day on Tuesday.